Hello.
Yes, sir.
Yes, sir.
Yeah, hi. Good evening, guys. Okay, so we were discussing biomolecules. What have we done?
So you said we'll start Harvard structure.
Just a second, let me check. Okay, so in biomolecules, we have discussed cyclic hemiacetal structure. Okay, fine. So, okay, so we have discussed cyclic hemiacetal structure of glucose, and have we discussed epimers? Epimers definition you have written? Epimers and anomers?
So we only did anomers.
Am I audible? Yeah. Okay.
So we did the animal.
Epimers have we discussed? No?
No, sir.
No, sir.
Fine. So anomers definitions we have seen. So those carbohydrates which differs in the configuration only at the anomeric carbon. Anomeric carbon are those carbon which has OH and OR linkage, correct? So we have discussed that alpha D plus glucose and beta D plus glucose are anomers of each other. Okay. Similarly, we have one more term that we define that we call it as epimers. Okay. So write down the heading epimers. Write down. These are the carbohydrates these are the carbohydrates which differs in configuration only at one carbon other than the anomeric carbon. Okay, are called epimers. Okay, apart from anomeric carbon, other carbon we have a difference in configuration. For example, you see, if I write down the structure of glucose, hydrogen, hydrogen, and hydrogen. This is structure. And mannose. Mannose, if you see the structure is this CHO, OH, H. Then we have OH, H, OH, H and OH, H, and here we have CH2OH. Okay, the structure of galactose you see CHO, OH, H, H and OH. We have H, OH, OH and H. This structure, the first one that I have drawn, this structure is D-glucose, right? This structure is D-mannose, and this structure is D-galactose. Okay, you see in between D-glucose and D-mannose, the configuration differs at only second carbon, only this carbon you see, right? So these two are what? These two are epimers. Okay, and in this two also you see here and here, these two are also epimers because the configuration differs at only fourth carbon you see. All other configurations are same. So glucose and galactose are epimers, glucose and mannose are also epimers. Okay, what kind of epimers? You see the configuration differs at second carbon. So this is C2 epimers of each other. Glucose and galactose are C2 epimers of each other. Glucose and mannose are C2. Glucose and galactose are C4 epimers of each other. Clear? So epimers definition you must remember. Relation of glucose and mannose, glucose galactose, they are C2 and C4 epimers respectively. You must keep in mind. Done. Okay. Next, the other structure that we have to see, this we call it as Haworth structure of glucose. Haworth structure is given by a scientist called R.D. Haworth, and hence this structure is Haworth structure of glucose. So what he has done, he has taken a reference compound to define the structure of glucose. I want you to see the cyclic hemiacetal structure of glucose, right? That structure, if you see, you must have drawn the structure in the last class, cyclic hemiacetal structure. The cyclic structure is 6-membered ring, correct? Including that oxygen, yes or no? Okay, and the oxygen attached with which carbon atom? Fifth and first carbon atom, right? Oxygen attached with fifth and first carbon atom. Fine. So the reference compound they have taken for this is pyrene, and the structure of pyrene is this. Pyrene structure is this 6-membered ring, and we have a double bond here. So hence it is a 6-membered ring contain oxygen in the ring. So the reference compound is this, we call it as pyrene. Okay, so with respect to this, if I draw the structure of glucose, Haworth structure of glucose, that would be something like this. We have oxygen, and this, correct? Oxygen, like I said, it is attached with first carbon and fifth carbon. You see, sixth carbon is not the member of the ring, and this is the numbering we have. Okay, now you see, you have a structure like this, correct? Okay, OH on the right, H, OH, H, OH, and H. This is the structure. This structure is alpha D plus glucose. If you write this OH on the left, then it is beta. Okay. Now what you have to do, like you see the numbering here, it is 1, 2, 3, 4, 5, and 6. Okay. The atom or group which is written on the right side of this carbon atom, 2, 3, 4, 1, 2, 3, 4. Okay. So this atom present over here like this, H and OH. H and OH, right? So all those atom or group which is present on the right should be written on the bottom of this vertical line. So at the second carbon you see OH on the right, so we'll write down here on the bottom, H on the right, on the bottom, OH on the right, on the bottom. Fifth carbon we have OR one side, this is OR, H on the left side, so on the bottom.
So H will be on top, right?
H on the bottom, H on the left, no. So
The CH2H will
On
be
the
at the
right.
bottom.
we have CH2OH here
Oh, okay.
and H here. So just a second, bottom, top, it's correct only. OH on the right, on the bottom, H on the right, on the bottom, OH on the right, on the bottom. Correct. It's like this only. Okay. So we can do one more thing like this. First carbon, you let it be now. On the second carbon, OH on the right, second carbon, OH down, then third OH up, fourth OH down. Fifth, we have one group is CH2OH, another one is hydrogen, right? So CH2OH on the top and hydrogen on the bottom. Correct. So OH you have to write alternate, right? Or better you see H you have to write alternate. You see second carbon H on the top, you have to start from here. Then on the bottom, then on the top, and then on the bottom. Simple. Okay, second carbon, H on the top, then bottom, then top, and then bottom. And rest all other positions we have OH and CH2OH. OH, 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 and CH2OH. Okay. Now depending upon the structure here, whether it is alpha or beta, we know in alpha OH on the right and beta OH on the left. So if it is alpha D plus glucose, then OH is here and H is here. Okay, when you write down this OH on the bottom on the first carbon, this becomes alpha D plus glucose. Okay, if I draw the structure of beta D plus glucose, that would be this. We have everything is same, only the difference we have on the first carbon. Okay. At the second carbon, third carbon, fourth carbon, and fifth carbon, we have H on the top, H on the bottom, H on the top, H on the bottom. Then OH here, OH here, OH here, and fifth carbon we do not have OH, but we have CH2OH. The first carbon, since it is beta, so H down, OH up. So it is beta D plus glucose. Is it clear?
So could you give 2 minutes to note this down?
Yeah.
Sir, in the fifth carbon, isn't hydrogen on the left? So shouldn't it come up?
No, it's not. That first and fifth carbon, you let it be. You don't consider like we are doing for 2, 3, and 4. Actually, on the right side, we have OR group. Okay. So the logic that we are taking at second, third, and fourth carbon, the same logic you don't apply on fifth carbon.
Okay, sir.
Okay. That's why it's better to consider that H wala factor in mind. Okay. Second carbon, H on the top, then bottom, on the top, and then bottom. And rest all position we have OH present. Only we have to take care of at fifth carbon, because at fifth carbon we don't have OH, but we have CH2OH. Correct? It's not like that is the logic that I told you, that right, then bottom, left, and then top. It is not any logic. This is just a way to memorize it. That is it.
Okay, sir.
Okay. Fine. So it is alpha D plus glucose, beta D plus glucose. Since this structure is, defined on the basis of this structure, which is pyrene. So name of this compound is, we call these compounds as glucopyranose. Glucose and pyrene. So it is glucopyranose. Okay. So whenever you see this glucopyranose, it means we are talking about the Haworth structure of glucose. If you write alpha D plus beta D plus, then it is cyclic hemiacetal. It is D plus glucose, then it is open chain structure, not a cyclic compound.
Sir, are both together called glucopyranose or just like either one of them?
No, the general term is glucopyranose for this one. Alpha, beta for both we call it as.
Oh, okay, sir.
Because both structures are drawn with pyrene. So it's a general term of Haworth structure, which includes both structure here. Correct?
Yes, sir.
Okay. Now I told you one thing also, that beta form is the more stable form over here. More stable form. Here you see when both OH on the same side here in alpha form, they experience diaxial repulsion. Diaxial repulsion. Because both OH are present on the axial bond. So there is a diaxial repulsion, and because of that only it is not stable. And hence in solid state, glucose exists in beta form. Done? Okay. The next, write down cyclic hemiacetal structure of fructose. Cyclic hemiacetal structure of fructose. Okay, so let's draw the structure of fructose first. We have CH2OH on the top, then we have C double bond O, and here the configuration is same. Third carbon we have OH on the left side, then OH on the right, OH on the right. Here we have CH2OH, H, H, and OH. To get the cyclic hemiacetal structure, this oxygen of this fifth carbon takes part in the bonding. This comes over here, and this H plus is taken up by this oxygen, which is the same thing we have in glucose also. So what we get carbon with OH or CH2OH. Okay, and here we have H, OH, and this is attached with this oxygen here. CH2OH on the bottom. H, H, OH. Similarly, we can have one more structure possible where the carbon has CH2OH on the right, OH on the left, and here we have H, OH, OH, H, OH, H, and on the bottom we have CH2OH. Okay. This structure that I have given you here, obviously it is D configuration, D minus fructose. Dy because OH on the right here. Minus is the experimental information we have. This one is OH on the right. Again, it is alpha D minus fructose. And this one is beta D minus fructose. Draw these three structures.
So why did you join the O here with the C to form cyclic structure?
Which one?
For beta D fructose?
Oh, achha, I missed it. Sorry.
Okay.
Yeah.
So what's the minus?
Sorry? D minus, yeah.
So
Negative.
what does it signify, the minus?
See, I have already discussed the same thing in case of glucose, which was D plus glucose, correct? Right. So both are optically active compound. So their behavior towards PPL is signified by this positive and negative sign.
Oh, so this is the absolute thing.
Yeah, it is absolute, correct.
Okay, sir.
It is the actual behavior of the molecule. And this information, whether it is plus or minus, means the rotation is clockwise or anti-clockwise of the PPL that we get when we do the experiment with the polarimeter. Correct? So here you see what happens in this. If you number the carbon atom, we have first, second, third, fourth, fifth, and sixth. 1, 2, 3, 4, 5, and 6. So we have 6 carbon atom, but the ring that we are getting here, the cyclic ring that we are getting here is a 5-member ring. Okay, just exactly similar to that of glucose that we have discussed. Okay, there we have 6-member ring. Here we have 5-member ring. Okay, so 5-member ring where oxygen is attached with the second and fifth carbon. Correct. So similarly, Haworth also given the structure of fructose, and that we call it as the Haworth structure of fructose. Okay, so write down the next Haworth structure. Okay, so here the reference compound is to define the structure of fructose is furan. And furan, the formula is this. Okay. With this, if you draw the structure of fructose, the structure would be this. Okay. This is because oxygen attached with second and fifth carbon. This is second and this is fifth. Third here and fourth here. Second, third, fourth, and fifth. Okay. Now, if OH on the right on the second carbon, then it is alpha form, right? So OH on the right, so we must write OH here on the bottom. So I'll just start from this. We have OH on the bottom, and on the top we have CH2OH. Here you see third one, OH on the top, H, then OH on the bottom, H, then on the fifth carbon we have H here and CH2OH here. If you look at the cyclic hemiacetal structure of fructose, you'll get this only. Okay, when OH on the down, it is alpha D minus fructose. In case of beta, what happens? At second carbon, CH2OH on the bottom, OH on the top. Clear? This
So your
structure is,
alpha will be more stable, right?
Hmm?
Alpha will be more stable, right?
Why?
Because same thing, right? OH, but then
OH on the opposite side, so alpha is more stable than beta, correct? It is beta D minus fructose. Okay, understood this structure. Now, the common name of these two structures are what? The common name is, it is fructofuranose. Okay, so glucopyranose and fructofuranose, the common name of this. Now, one more thing, what happens, and this question they have asked once, okay, in JEE exam, that the correct structure of fructose, beta D minus fructose, the correct structure of this, okay? Suppose I draw this structure, oxygen, here we have CH2OH, H, OH, H. Just a second. Yeah, I made a mistake. OH, H, HOH, and then here we have CH2OH and H. This structure is correct or not?
No, sir.
No, sir.
It's not correct
So
because
the number of OH things on this is different.
right, the position of H and OH is different, correct?
Even the
But-
number of hydroxy groups.
No, number of hydroxy groups are same. No, just a second. Just a second.
there should be 3.
If you do this, I'll just do one change here. If I place oxygen here, then OH.
So it'll be beta D minus.
It is beta D minus fructose. It is beta D minus.
So no, sir.
Why?
So because this is, if we turn everything the opposite way, HOH position will also change. If you're looking at it that way.
Yeah, so I think this is neither.
With respect to CH2OH, the other HOH will be opposite.
What if I write this as the second carbon? This is third. This is fourth, and this is fifth.
So,
It
but in
will
none of
be-
the others, you have two consecutive OHs on the bottom.
But on the top we have no.
Yeah, if you turn it around, it's gonna be.
Yes, sir, it's beta D minus.
Yeah.
If you flip this structure, right? If you flip this, then we get this, no?
So you're not allowed to do that with optically active compounds, right?
Sorry?
So you can't just split the molecule, right? That's not allowed when you're talking about optically active
No.
compounds.
That is for to find out the optically active nature of this molecule. let's forget it. If you're getting it, if you're getting confused over here, let it be.
So
If
it is,
just a second,
looks like fructose, but I don't know about beta D minus.
just a second. See, suppose you are looking at this molecule from the top now, right? Suppose it is a three-dimensional structure. This bond is a thick wedge we have coming towards you, right? Coming towards you, three-dimensional structure. Now, if you're looking from the top, you see this OH on the second carbon is coming up, third carbon OH is coming up, fourth carbon H is coming up, fifth carbon CS2 OH is coming up, correct? Now, when you change the view angle, if you go down and when you look at this molecule from the bottom, you can say at the second carbon OH is going away, third carbon OH is going away, fourth carbon H is going away, and CS2 OH is going away, right? Which is nothing but this representation, yes or no?
Yes, sir.
Right. So in these two molecules are exactly same. There's no difference in these two. Only the view angle is different. One of the molecule we are looking at from the top, same molecule. If you look that molecule from the bottom, you'll get this structure, correct? Or we can say what, if you flip this, we are not talking about the optical active nature of it, right? If you flip this molecule, means second comes at the position of fifth, fifth comes at the position of second, third comes here, fourth comes here, and the atom or group which is coming on the top over here, which is placed on the top on these bonds, should go on the bottom now, right? So OH on the top we have on the second carbon. When you flip this at the second carbon, OH will go down. Fifth carbon, H is here in the bottom, H is here in the top. So in these two structures, first of all, both are exactly same structure. When you flip this, you'll get this. You can understand this way, or just the view angle you can change. Both looks like the same molecule. Yes or no? So if you don't number this, suppose you don't number this 1, 2, 3, 4, 5, 6, right? Then what we are expecting that this corner is always second carbon, and hence OH will be on the top. Are you getting my point? Right.
Yes, sir.
So this structure, if you draw, obviously they won't number the carbon atom. They'll simply give you this structure. So this structure is also correct. Don't think that this carbon is the second carbon always. And here we have always OH present for beta D minus fructose. Right? So on flipping of this molecule, once they have asked question in JEE exam, okay, the correct structure of fructose or something like that. Okay, so students they were expecting that this is a second carbon always. So here we should have OH on the top, which is not there. So they were thinking that this structure is wrong, which is not the case here. Did you get it?
Yes, sir.
Okay, so this is the Haworth structure of fructose. Okay. All these cyclic structures, hemiacetal structure, Haworth structures, exist in solid form. Okay, when you place this in water aqueous form, this molecules, whether it is fructose or glucose, this goes under hydrolysis and converts into D minus fructose or D plus fructose. When I say D plus fructose means what? It is a straight chain compound, right? There's no cyclic ring structure into this. Got it? So in aqueous medium, it will be in that form, a straight chain compound. Solid state, this is the structure we have here. Okay. Based on this only, the hydrolysis concept, one more concept we have to understand here, and that concept we call it as mutarotation. Write down. Mutarotation. Write down. The spontaneous change in the specific rotation value, the spontaneous change in the specific rotation value of an optically active compound is known as muta rotation.
So could you repeat?
Sorry?
So could you repeat?
Yeah. The spontaneous change in the specific rotation value. The spontaneous change in the specific rotation value of an optically active compound is known as muta rotation. Is known as muta rotation. Okay, so you see we have alpha D plus glucose, suppose, and when I write alpha D plus glucose means it is the Haworth structure, cyclic hemiacetal. Okay, cyclic hemiacetal structure of this. When you dissolve this in water, then what happens? Acidic hydrolysis, it is H plus H2O. Hydrolysis takes place and alpha D plus glucose converts into D plus glucose. Is it right? Right. And from this D plus glucose, it can also form the ring structure, that is a cyclic hemiacetal structure. And cyclic hemiacetal structure, there is possibility that this would convert into beta D plus glucose, correct? Alpha may also form, but beta may also form. So point I'm trying to make is what? In aqueous solution, this alpha D plus converts into D plus glucose, open chain structure, and then it has possibility to convert into beta. So what we can say, in aqueous solution, we have an equilibrium between alpha D plus glucose and beta D plus glucose. Equilibrium in the sense of what you see. If you look at the specific rotation of alpha D plus glucose, which is again an experimental value, you don't have to memorize this, 111 degree. For this one, the specific rotation is,
What do you mean by specific rotation?
it is plus 19 degree. It is the angle by which this rotates the plane polarized light. Wait, Dhruv, I'll explain. That is what I'm explaining here, okay? I'll dictate the definition, just a second.
Okay, sir.
Okay, so a specific rotation is the angle by which the plane polarized light rotates when it passes through an optically active compound. Right, plus minus represents clockwise and anti-clockwise simply. So for alpha D plus glucose, it is plus 111 degree. Beta D plus glucose is plus 19 degree. These two exist in equilibrium and they try to maintain an equilibrium value of specific rotation. Equilibrium value of specific rotation. And the equilibrium value here for specific rotation of this mixture is 52.5 degree. So this phenomenon of change in specific rotation, spontaneous change in a specific rotation, is called muta rotation. Conversion of alpha into beta, beta into alpha takes place simultaneously till the equilibrium value is this, maintained to be this. This is muta rotation. So the definition of muta rotation, through write down the spontaneous change in a specific rotation value. The spontaneous change in a specific rotation value
Yes, sir.
of an optically active compound is known as muta rotation.
Done, sir.
Done?
Yes, sir.
Okay. So this is the one concept we have. Okay. Now the another one is how to differentiate glucose and fructose. That's what here it is written, no? D first of all, D and L is different from plus and minus. D is the theoretical method we have. Okay. It has no relation with D and plus. Like we have E is not always cis. Z is not always Z is not always cis. E is not always trans. Both are different way to represent the configuration, right? Similarly, DL and plus minus are also different. It's not like D is always plus or L is always minus. Okay, yeah. Now the next thing here is how to differentiate glucose and fructose. Means suppose you have a given compound carbohydrate and you have to find out whether it is glucose or fructose. How do we do that? Right? So how to differentiate glucose and fructose? Okay, now to understand this, you should know the basic difference between glucose and fructose. So what is the basic difference between glucose and fructose we have?
Primary functional group.
Basic difference between glucose and fructose is glucose has aldehyde as the primary functional group and this has ketone as the primary functional group. Right. So it shows the reaction of aldehyde or properties of aldehyde mainly. This shows the properties of ketones. Because aldehyde and ketone are the major functional group here. We have primary functional group. Okay. Now to understand this, how to differentiate the two molecules here, you should know the reaction of glucose and fructose. what all reactions we have for glucose and fructose, and how reaction we have for aldehyde and ketone, and how do we differentiate aldehyde and ketone. That is it. Okay, with that we can do this. So to differentiate aldehyde and ketone, what we use a property, and that property is what? The oxidizing nature. Is the oxidizing nature. If you look at the oxidizing nature of aldehyde, aldehydes are easily oxidized. But ketones, oxidation is not easy. It's not easy. Oxidation of ketone takes place in a very drastic condition. Okay, acidified KMNO4 K2Cr2O7 we can use for this purpose. Okay, but oxidation of ketone is difficult in comparison to aldehyde. Okay, so obviously what we need, we require a mild oxidizing agent, right? Because oxidation of ketone requires very strong oxidizing agent because it is difficult to oxidize. But aldehyde can be easily oxidized. So we can oxidize aldehyde with mild oxidizing agent, but for the ketone we required very strong oxidizing agent. Right. So obviously, if you have to differentiate between the two, we can take mild oxidizing agent. And if the reaction is taking place, oxidation is taking place, then we say it is aldehyde, not ketone. Okay, that is the basic idea we have here. Correct. So the solution that we use, or the method that we have here to differentiate this aldehyde and ketone, is we use Fehling solution. Okay, Tollens reagent, all these things we can use, okay, to differentiate aldehyde and ketone. Okay, okay, write down, to differentiate aldehyde or ketone, we can use, or we use, first test is Tollens reagent test. We use Tollens reagent test. We also use Fehling solution test. Fehling solution test. One more test we have, that is Benedict solution. We can use this. Remember here, I'm not talking about glucose and fructose now. I'm just trying to give you an idea of aldehyde and ketone. And then we'll go back to glucose and fructose. With this two tests, we can differentiate aldehyde and ketone. These are mild oxidizing agent. Oxidizes only aldehyde. Oxidizes only aldehyde. Okay, not ketone. Oxidizes only aldehyde, not ketone. And the medium for this oxidation is basic, alkaline medium we have. Okay. So what happens if you have an aldehyde RCHO with Tollens reagent, it converts into acid, and with failing solution, it again converts into acid. I am not going into detail of this reaction because we'll do this in the next chapter of oxidation reduction. Grignard reagent and oxidation reaction. We'll do this reaction in detail over there. Okay, just to keep in mind that these reagents oxidizes the aldehyde into acid. That is it. Right. If you have ketone R C double bond OR. Okay. So this with Tollens reagent and failing solution, we have no reaction here because it cannot oxidize ketone. Okay. Now we can use this concept to differentiate aldehyde and ketone. Okay, and ketone, because ketone I should write here glucose and fructose. Okay, to differentiate glucose and fructose, since fructose contains ketone, and this contains aldehyde, glucose. Hence, by this reaction, we can differentiate the two. Okay, but actually when we try this, then what happens? Write down this note. Fructose contains ketone group as the primary functional group. Fructose contains ketone group as the primary functional group. Then also it gives positive Tollens. Then also it gives positive Tollens and filling solution test. Positive Tollens and failing solution test. Hence, we cannot differentiate glucose and fructose by this method. Did you get it? You must understand this because this is important. Okay, they ask question on this.
Can you repeat it once?
I said what? See, the last line you are talking about.
Yeah.
Fructose contains ketone group. Then also it gives positive Tollens and filling solution test. And hence we cannot differentiate glucose and fructose by this method. Okay, So our expectation was what? Our expectation was that fructose has ketone and glucose has aldehyde. So the way we differentiate aldehyde and ketone, similarly, we can differentiate glucose and fructose, right? But this is not happening here, right? In fact, this is a very common question they have asked many times in the exam, that which of these group does not show positive tolerance or failing solution test. One of the option is fructose, because we all know fructose has ketone as a primary functional group. It is the only molecule, only ketonic functional group here, which shows positive tolerance and failing solution test. So most important, do not forget it. Okay, fructose shows positive tolerance and failing solution test. Now, why it is happening? That is the reason, right? Why fructose gives positive tolerance test, right? Although it contains ketone as the primary functional group, correct? That is what we need to understand. So first thing here, it is what? That we cannot use tolerance reagent and failing solution test. Then what we should use? What method we should use to differentiate the two? That is, a question, a live question we have. And that is the question we are trying to understand this, okay? First, we need to understand that why this is not happening with fructose and what reagent we use to differentiate the two molecules. What is the criteria on which we choose the reagent to differentiate the two, okay? So first we'll understand why fructose gives this test, tolerance reagent test and failing solution test, okay? So heading, you write down why fructose gives positive tolerance and failing solution test, okay? Let me draw this structure here. Here we have glucose, C double bond O, H, OH, H, OH, OH, and CH2OH. Okay. This compound is D-glucose. This is D-mannose. And this is D-fructose. Okay. So the point here is what? That this glucose, mannose, and fructose. We have glucose, mannose, and fructose. All these three compounds exist in equilibrium in alkaline medium. Right, when the medium is alkaline here, OH minus. Right. So if you take fructose for the test, right, this fructose has ketone as a primary functional group, but since the medium of these tests, Tollens and Felling, is alkaline, this fructose converts into glucose and mannose. Right. So what happens here, you see, if you have a beaker in which you have taken fructose for the test. Okay, so in the beaker we have fructose. Medium is alkaline for this Tollens test, TR, OH minus. So because the medium is alkaline, this converts into glucose and, just a second. Okay, medium is alkaline, so this converts into fructose, converts into glucose and mannose, right? Tollens reagent, OH minus medium. You see this, both glucose and mannose has primary functional group as aldehyde. This is also aldehyde. So you have taken fructose initially, but it converts into glucose and mannose, which has aldehyde as a primary functional group. Hence, the mixture here, the solution, shows positive test. Did you get it?
So can you repeat it once?
Since fructose you have taken, but actually in the solution we do not have only fructose. But what we have a mixture of glucose, fructose, and mannose, right? Because it converts into glucose in alkaline medium. Because of this conversion only, the solution overall shows positive test.
Okay, sir.
So could you go back to the previous slide?
Okay, this is the reason we have why fructose shows positive Tollens test.
So Tollens test and Felling's test happen in alkaline.
Sorry, Vikas?
So do Felling's test and Tollens test happen?
Your voice is breaking, Vikas. I'm not getting you. Come again?
So do Felling's test and Tollens
Felling's-
test happen? Do
both.
they happen in an alkaline medium?
So he's asking if both Felling's and Tollens test happen in alkaline medium.
Yes, both. Both tests takes place in alkaline medium. Okay? I am not going to make you understand those tests, because anyways we are going to understand those reactions in the next chapter. Okay, so as of now, like for now, you just let it be. Okay, that reaction, how it happens, what is the mechanism, we'll discuss that later. Okay, Tollens test, we also call it as silver mirror test. Okay, you want to keep this particular thing in mind, you can keep this, okay, for now. But mechanism and all, we'll discuss that, okay, in the next chapter. Okay, so how it is happening, first of all, you see, we know the reason that this equilibrium exists. So fructose converts into glucose and mannose, and hence the solution overall shows positive test. But how it is happening, there is tautomerism here. One, you see here, I'll just write down this, this part of glucose, which is nothing but this structure we have. C double bond O, H, OH, H, and this is the same we have here, correct? So between 1, 2, and 3, among these 3 atoms, okay, we have tautomerism, correct? So what happens? This pi electron comes over here, and this H will get attached onto this oxygen. So what we get, you see, carbon has OH on one side, H this side, double bond C, OH, and this thing will be as it is. Okay. Again, what happens? Again, what happens? You see, between among one. Just a second. Among 1, 2, and 3, again tautomerism takes place. So this comes over here, and this hydrogen comes onto the first carbon. So on the top we have CH2OH, and the second carbon will have this O, and rest is as it is. So this is nothing but fructose. This is fructose. Like how this fructose and glucose are interconvertible. Got it? Did you understand this?
So what about manuals?
I'm coming to that. This
Okay.
part you understood?
Yes, sir.
Now you see, these two are interconvertible. If this converts into this, since it is reversible, this also has tendency to convert into this. Correct? How it happens? From here, H comes out and get attached onto this carbon. Then this pi bond goes here, we'll get this. But since this carbon, you see, this carbon is sp2 hybridized. So this hydrogen which gets attached to this carbon atom, it can attack from this side or from this side, both sides. If this hydrogen gets attached from this side, then this OH will be on the left side of it. And hence, this is the structure we get. Correct? Why it happens? Because the second carbon becomes sp2. It was sp3 here, but here it becomes sp2. And since it is sp2, so this hydrogen can attach from this carbon from both sides. If it attached from this side, then we get glucose. If it attached from this side, then we'll get mannose, which is the epimers of glucose. Clear now?
Yes, sir.
Right. So that is what the reason we have why fructose shows positive Fellings and Tollens reagent test. Okay. Okay. One more thing we'll just see here, which is important. This two we have discussed. These two are what? C2, epimers, and D-glucose and D-fructose are what? Tautomers. Okay, so write down D-glucose and D-fructose are tautomers of each other. D-glucose and D-fructose are tautomers of each other. Correct? Now, so we have discussed this, why fructose shows positive Tollens and Fellings solution test. Okay? This rearrangement we call it as Lowry D Van Bryan Ekenstein rearrangement. This reaction is this Lowry D Van Bryan Ekenstein rearrangement.
So how many people are there in that rearrangement, the name?
I think I'm not very sure with it, but I think two people are there. Lobby D Van Bryan is one. Lobby D Van is one, and Brian Inkenstein is the other people we have here. Two people are there.
Okay, sir.
Just a second. Yeah. So this is the reaction we have. Okay. Now, one thing is for sure that whenever you use any oxidizing agent, which medium is alkaline, right? So whenever it is alkaline medium, OH minus, okay, then this equilibrium exists among the three, okay, fructose, mannose, glucose, and these three, right? So any oxidizing agent whose medium is alkaline, we cannot use to differentiate glucose and fructose. Is it clear? Right? Hence, what we use bromine water for this purpose. Okay, so write down the note here. Now, to differentiate glucose and fructose, we cannot use an oxidizing agent whose medium is alkaline, and hence we use bromine water for this purpose. And hence we use bromine water for this purpose.
Wait, sir, could you repeat that?
Sorry?
Sir, could you repeat the previous sentence?
Now, to differentiate glucose and fructose, we cannot use any oxidizing agent. Whose medium is alkaline, and hence we use bromine water bromine water for this purpose. Done.
Thank you, sir.
Okay. So this is the reason we have. Next, write down the reaction of glucose. Reaction based question, usually they ask in the exam. Okay. So this one is also important. Write down reaction of glucose. So again, you write down this in one complete full like blank page, because again, we'll write down all the reactions in one single page. Okay. So heading, you write down the reaction of glucose. See the oxidation of bromine water. First of all, you see this uh, the medium is not alkaline, which is the biggest advantage we have for bromine water. Plus, it is also not very strong oxidizing agent. Bromine water is not that strong. Okay, hence it can oxidize only aldehyde, not ketone. Mechanism, like I said, I am not discussing now. Mechanism we'll see in the next chapter. Here it is not required. Okay, but the two advantage we have, it is not very strong oxidizing agent. Plus, this medium is not alkaline. Okay, yes. So this is the thing. Now the reaction of glucose, you write down. The structure of glucose here is C double bond. You also write down this way only. C double bond OH. One, two, three, four. CH2OH. Here we have OH, H, OH. Okay. Now, when this reacts with NaBH4, NaBH4, okay, it is a reducing agent. NaBH4 is a reducing agent, and it reduces aldehyde into alcohol. And the product that we get here is, on the top, instead of CHO, we'll get CH2OH. 1, 2, 3, 4, and here we have CH2OH. All other things, it is same. Okay, there is no change on this. Okay, this is the first reaction, reduction of NaBH4. Okay, so we have okay. Now the second reaction is if you are taking HNO3. HNO3 is a strong oxidizing agent here. HNO3, it is a strong oxidizing agent and it converts primary alcohol and aldehyde into acid. Okay. Primary alcohol first oxidize into aldehyde and then it oxidizes into acid. Okay, this is the compound we get. And this compound we call it as saccharic acid. The second reaction. Third reaction, you see, when you allow this to react with an oxidizing agent, which is Tollens reagent, okay, failing solution, or with bromine water, it oxidizes this into acid, but not alcohol, CH2OH here. This molecule, we call it as glucaric acid. Glucaric acid. Okay. This on reaction with hydroxylamine, that is NH2OH, it converts into oxime, NOH. This reaction we have already seen, and this is same.
What's the name of the compound?
Done. One more reaction we'll see in this, and that reaction is osazone formation. I'll show you that reaction. Wait. Okay. In osazone formation.
So can you repeat? I didn't get it.
Wait, I'll write down. Just trying to check. Yeah. Osazone formation, we use 3 moles of phenyl hydrazine. This reaction, where we're using 3 moles of NH2NH pH, phenyl hydrazine. Okay, so this reaction is very important. And this reaction, we call it as osazone, OSAZONE, osazone formation. Okay, 3 moles of this. So this question they have asked many times in the exam. How many moles of phenyl hydrazine we use in osazone formation? Osazone formation, the product of this reaction is this. C double bond N, NHPH, Here we have H. Here we have C double bond N, NHPH, NHPH, and this is same. H, OH, OH, H. Here we have OH, H, CH2OH. This compound, we call it as glucosazone. Copy this down. This is glucosazone. Done. You can understand this mechanism this way. Did you copy this? I'll go to the next page.
So just 1 second.
Okay.
Yes, sir, done.
All of you done?
Yes, sir.
Okay. Now, however, the mechanism of last reaction is not important. Okay. But I'll just explain a little bit of it. How do you can think about this reaction? We have glucose, right? So glucose is C double bond O, H, OH, H, and this part you let it be because it is not going to involve in this reaction. Out of 3 moles of phenyl hydrazine, 1 mole we are using in the first step here, NNH, PH, and 2 hydrogen we have here. So with this 2 hydrogen, it combines with oxygen and forms H2O, goes out. And it forms H, C double bond, N, NHPH. Carbon, OH, H, and rest will be as it is. Next we have tautomerism here. Tautomerism. And in this what happens? This pi comes over here and this H goes out on this nitrogen atom like this. Oh, I'm sorry. Not this H. It's 1, 2, 3 now. So this H comes out and this H will get attached onto this nitrogen. This will come out. Okay. This will come out and get attached with this nitrogen. So what we get here, you see, H, C single bond NH, NHPH. Double bond C, OH, and rest will be as it is. Further, what happens? This H plus comes out, leaving this bond pair of electron behind. This comes over here, and this comes out as a leaving group when this forms a double bond here. So when this comes out as a leaving group, this takes this hydrogen and it converts into H, C double bond NH, C double bond O plus PH NH2. And here the things will be as it is. Now here, the rest 2 mole of phenyl hydrazine we are using for this process. Okay. Rest 2 mole, how do we use this? This 2 hydrogen takes this NH, forms NH3 and goes out. So we'll get 1 mole of NH3 here. How NH3? This 2 hydrogen here and NH forms NH3, goes out. And 1 mole we have used here, 1 mole we'll use here. With this H2 and O, it forms what? H2O. And the final product we get in this reaction is C double bond NHPH, C double bond N, NHPH, and rest is same here. OH on the left, again I am telling you the mechanism is not important. You must remember how many moles of phenyl hydrazine we are using for this purpose. Got it?
Tautomerism, ketoenol tautomerism, because it kind of resembles that.
Just a second, Vikas, just a second. Tell me what?
Sir, is the tautomerism ketoenol, because it sort of resembles ketoenol tautomerism?
Ketoenol.
So because we don't have a keto group, but there's a C double bond a group and
Kind of, you can say it is not ketoenol, but similar to that.
Okay, sir.
It is not ketoenol, that we cannot say, because we have H over here, but it is similar to that. Understood? No, if this H is not there, if it is R, then it is ketoenol.
Yes, sir.
Okay, similar to that. So this is what the mechanism we are. Remember, in the last step, we are using 2 moles of this. First step, we'll use 1 mole of phenyl hydrazine here. Okay, so apart from this glucosazone, this molecule is glucosazone. What all molecules we get? We get NH3. We get how many molecules of H2O? We get total 2 molecules of H2O, and 1 more molecules we are getting here. That is aniline. Plus pH NH2 also forms in this reaction. So apart from glucosazone, these 3 molecules also forms. Understood? Mechanism, again I am repeating, mechanism is not important for this. Number of this thing is very important. Which sentence, Kritika?
Sir, I got it. It's fine.
Okay, fine. Right. One more thing you see, this reaction we have OH here, H here, OH, OH. How many stereoisomers possible for this? This is also one kind of question they ask. Stereoisomers based question they ask in this particular chapter. Okay, depending upon the structure. So we have how many chiral center in this molecule? 4 chiral center, yes or no? Okay, we have 4 chiral center present here. Four chiral center. So number of stereoisomers. What formula we use? We use 2 to the power n minus 1 plus 2 to the power p minus 1. 2 to the power n minus 1 plus 2 to the power p minus 1. Where p is equals to what? P is equals to n by 2 if n is even. If you remember this formula, we have done this in isomerism. If n is even, okay, we use this formula when the ints of the allenes are same. Remember this one, right? Ints is CH2OH here, and here also it is CH2OH. So ints are same, so we use this formula. Okay, so p value will be, n value is 4, so p is 2. So number of stereoisomers will be 2 to the power 4 minus 1 plus 2 to the power 2 minus 1. that is 10 stereoisomers possible for this. It is not 8. Right, just we are using the formula. This formula we have done in isomerism. Keep that in mind. Okay. If you use fructose here, again I am giving one very important reaction. With fructose also, you will get the same product, because NaBH4 can reduce aldehyde as well as ketone. Okay, so write down this note. NaBH4 can reduce aldehyde as well as ketone, and then after this you write down the reaction of fructose with NaBH4. I forgot to write here, it is H plus H2O. With NaBH4, in the second step we use H plus H2O also here. This is the first step, and in the second step we use H plus H2. We'll see this reaction also next chapter. Okay. So if you're using fructose, correct? So the fructose molecular formula is CH2OH, C double bond O, OH on the left, OH, H, OH, H, CH2OH with NaBH4 H plus H2O. This gives CH2OH. Alcohol will be as it is. This carbon, this ketone group also converts into CH2OH, and all other things are same. CH2OH. You see, exactly same molecule we are getting. The number of stereoisomers here also it is 10. Okay.
So could you go back to the slide once, please?
Yes. This one.
Yes. Sir. Yes, sir. Done. Thank you.
Okay. Another thing you see. If you use here fructose for osazone formation, instead of glucose, if you take fructose, then also the reaction takes place at the first 2 carbon. Right. Even we get, in that case also we get the same structure as the product. Okay. So look, you see here, this reaction of fructose with 3 molecules of NH2, NHPH. 3 molecules of NH2, NHPH. In this also we get C double bond N, NHPH, H, C double bond N, NHPH, and this thing we have the same thing here. So this structure and glucosazone structure is exactly same, right? We also call it as fructosazone, since it is obtained from fructose. So glucosazone, fructosazone are the same molecule, but preferably we use glucose when it is formed with, preferably we use glucosazone when it forms with glucose. If it forms with fructose, then we'll call it as fructosazone, but glucosazone, fructosazone are the same molecule.
So in the first product, it should be CHOH, not CH2OH.
Where? On the top?
Yeah, so the NaBH4 reaction.
Here we have CHOH, correct. We'll see this reaction of in aldehyde ketone chapter also. And in aldehyde, in alcohol also we have this reaction. Okay, alcohol, 1 degree alcohol on oxidation gives aldehyde. Further oxidation takes place and it converts into acid depending upon how strong oxidizing agent we have. Okay, so 1 degree alcohol on partial oxidation gives aldehyde. 2 degree alcohol on partial oxidation gives ketone. On oxidation gives ketone. If you have very strong oxidizing agent in excess, then 1 degree won't give you aldehyde, but we end up getting acid in that reaction. We'll see these reactions. Okay, so these are the reactions of glucose. Okay, so the reaction based question, right? And number of stereoisomers, all these are very common questions in biomolecules. For biomolecules and polymers, you are going to have one question, max to max, not more than that, right? So the chapter is quite big. There are a lot of things to memorize here, but its weightage is not that great as far as J is concerned, right? So it's very important to study the selective things into this. Especially you should know what all things are important so that you can revise before the exam. Monosaccharides we have done. Okay, in the coming Chemon test you have on 20th, right, or 21st?
20th.
20th you have to study till here, monosaccharides. Okay,
So
now
including this topic?
Yes, this topic till monosaccharides, correct? Now we are going to start disaccharides. From here onwards you are going to have this portion in the next Chemon test. In fact, in next Chemon test, you're going to have the entire biomolecules. Clear? But for coming Chemon, till monosaccharides, we have to study whatever we have done till now. Got it? Okay, disaccharides, we know these are the compounds which on hydrolysis, write down, which on hydrolysis gives gives 2 units of monosaccharides. Two units of monosaccharides.
Sir, how many classes does this chapter take?
Till here, no, there are a lot of structure we need to draw in disaccharides also, right? But after finishing disaccharides, it is not much. Okay, I think we can almost finish this chapter in today's session. Okay, but next session, if max to max, next session, 1 more hour will take, not more than that.
Okay, sir.
Okay. So disaccharides. We have various examples. For example, we have sucrose. Sucrose on hydrolysis gives what? Sucrose on hydrolysis?
Glucose and fructose.
Glucose and fructose. Okay. Maltose gives 2 units of glucose, and galactose gives 1 unit of glucose and 1 unit of, it is lactose gives 1 unit of glucose and 1 unit of galactose here. Correct? These are the examples of disaccharides. Now, in this section, they ask very specific questions. Okay, when we say sucrose gives glucose and fructose, it's very general statement. What glucose we are getting? Are we getting alpha D glucose, beta D glucose, or beta D fructose, or alpha D fructose? Right there. So there are many possibilities we have here. So here the question that they ask, since this glucose we know, it is the combination of 1 unit of sucrose is 1 unit of fructose and 1 unit of glucose. So how this glucose and fructose gets connected? Which carbon atoms are involved in this reaction? Right. So which carbon atoms involved into this? That is one point. Okay. Between glucose and fructose, if we are talking about sucrose here, since we know it is made up of 1 unit of glucose and 1 unit of fructose. So which carbon atom is involved into this too? The carbon atom involves, the bond forms there. What kind of bond is this? Okay, what is the name of that bond? Right, depending upon the carbon atom involved, we can say the given sugar is reducing or non-reducing. Reducing sugar are those sugar which can reduce Felling's and Tollens solution. Felling's solution and Tollens reagent. Right. So how do we get to know about these the answer for these questions? Okay, that is what you need to memorize. Like I said, it's a very they ask very specific questions in this particular topic. Okay, 3-4 different types of question forms, and that is it. Okay, so the first point you write down, one note in this first you write down, one note in this you write down first. Write down in disaccharides. In disaccharides, monosaccharides are joined together monosaccharides are joined together by glycosidic linkage. GLYCO SIDIC, glycosidic. Monosaccharides are joined together by glycosidic linkage. So this glycosidic linkage, right, you should know that it forms between which carbon atom? Which carbon atom is involved into this? Right, that is the question they ask. Okay, now the first thing you write down here, we have sucrose. Write down, it is formed by the condensation of alpha D glucopyranose
So alpha D.
Glucopyranose have earth structure. Alpha D glucopyranose and beta D fructofuranose. Alpha D
Sir, is it D plus?
yes, beta D fructofuranose. Okay, so till now we were talking about what? Sucrose is made up of glucose and fructose, but alpha form of glucose and beta form of fructose we take into this. This is the point you need to memorize. First thing is this. Okay, next point to write down, formed by the condensation of alpha D glucopyranose and beta D fructofuranose, in which C1 and C2 carbon, carbons are involved respectively. In which C1 and C2 carbon are involved respectively.
Can you repeat that point?
Yes, I'm repeating it from the beginning. Just a second, I'm getting an urgent call. I have to pick it. Hello. Yeah. It is formed by the condensation of alpha D glucopyranose and beta D fructofuranose, in which C1 and C2 carbon atom are involved. Next, one more line you write down. The glycosidic linkage forms between the C1 carbon of alpha D glucopyranose, C1 carbon of alpha D glucopyranose, and C2 carbon of beta D fructofuranose. So this is important. They ask this question directly. The glycosidic linkage forms between, regarding with respect to this carbon atom, they'll give you 4 options between C1 and C2, C3, C4, like that. Okay, they'll give you 4 options. This you have to memorize. Now we know the structure of alpha D glucopyranose and beta D fructofuranose. So we'll try to write down the structure of these two, and then the condensation reaction takes place. We'll get the structure of sucrose. Do you know what is condensation reaction? Any idea of condensation? What is condensation reaction? See, condensation reactions are those reactions in which the smaller molecules like NH3, H2O eliminates. Simple, that is it. Okay? Those reactions in which the smaller molecules like water or NH3 eliminates. Kind of dehydration, you can say. Okay? So, this is one structure. Alpha D glucopyranose. Could you tell me here, this carbon atom is what carbon atom? This is what?
First.
C1. Right, so it is C1 carbon atom, first carbon. This carbon atom is what? Fifth, 4, 3, and 2. Not required here, this number to write down, but if you write down, you will memorize the structure. Okay, that's why I have written. So when you draw the structure, alpha D glucose, so what should we write on the top here? Could you tell me? And what we should write on the bottom?
OH at the bottom.
H on the top, OH on the bottom. Here, what we should write?
H at the top and OH at the bottom.
So H on the top, then alternate, correct? H on the bottom,
Yes, sir.
then H on the top, and
OH
then
at the bottom.
H on the bottom. OH on the bottom, here OH on the top, OH on the bottom, and fifth carbon has CH2OH. It does not have OH on this. So this is alpha D glucopyranose. You don't have to memorize it. Okay, we have drawn this structure so many times, right? You can easily memorize all these structures, correct? Alpha D glucopyranose. Now, beta D fructofuranose is what? Beta D fructofuranose is this. We have 5-member ring, correct? And this is the structure. Beta D means on the top we have this carbon is C2 or C1? This one.
So 2.
C2.
sir.
So we have OH on
it's
the top
hydrogen. Yeah.
and CH2OH on the bottom. This is the first carbon, this is the second carbon. Correct? At third carbon, OH on the top, H on the bottom. Fourth carbon, OH on the bottom, H on the top. Fifth carbon, H on the bottom, and CH2OH on the top. If you number this carbon atom, it is 1, 2, 3, 4, 5, and 6. Any doubt in this? No doubt in the structure, correct? Now, since this 2 goes under condensation reaction to form sucrose, so elimination of H2O takes place here. And from which carbon involves in the reaction here? C1 of
Alpha D.
alpha D glucopyranose and C2 of beta D fructofuranose. So HNOH comes out like this, forms H2O molecule, and these two molecules joins by these two carbon atoms, right? So I'll draw the structure here. The entire structure we get is this. Every other thing will be same. There's no change in this, and the structure is this is connected with oxygen, right, which goes down. Here we have one oxygen, and this is the structure we get. Okay, every other thing is same. CH2OH on the bottom, H on the bottom, OH on the top, on the bottom, H on the top, H on the bottom, and CH2OH on the top. Here also it is H on the top, OH on the bottom, H on the top, OH on the top, H on the bottom, then H on the top, OH on the bottom, H on the bottom, CH2OH on the top. This molecule is the compound that we get. This is sucrose.
So are there any particular conditions for this reaction to take place?
Particular
Like conditions?
No, we just heat it, or we can take acidic medium, not more than that.
Okay.
This is the Haworth structure of sucrose. Let me know once you finish it. Done?
Yes, sir.
Yes, sir.
Okay. Fine. Now, so the first question that they ask here, that glucose is made up of which two monomers, which two monosaccharides? Answer is alpha D sucrose is made up of alpha D glucopyranose and beta D fructofuranose. This is it. Second one, this linkage OO linkage that we have COC, it is, this linkage is glycosidic linkage. This is glycosidic S, glycosidic linkage. So this glycosidic linkage is present between which carbon atom? The C1 of alpha D glucopyranose and C2 of beta D fructofuranose. This again you have to memorize. Okay. If you remember, I have already told you that this structure is hemiacetal structure. Yes or no? What about this structure? What about this structure? It is hemiacetal. Okay, both are hemiacetal structure. Why hemiacetal? Because one OH and OR group is there. In this structure, you see, we do not have OH and OR, but we have OR and OR, OR and OR. So this structure is acetal structure. This is acetal structure. Two OR group attached into this. So sucrose has acetal structure, two OR group attached. One more thing that you can observe, that C1 carbon of alpha D glucopyranose and C2 carbon of beta D fructofuranose are anomeric carbon. Yes or no? Is it? These two are anomeric carbon. Yeah, these two are anomeric carbon. When anomeric carbon involved in glycosidic linkage, then the sugar is non-reducing sugar. When anomeric carbon is involved in glycosidic linkage, the sugar is non-reducing sugar. Right. For reducing sugar, any one of the anomeric carbon must be left there, must not involve in this glycosidic linkage. Any one. Right, any one. This is non-reducing sugar means what? Non-reducing means it cannot reduce tolerance reagent and Fehling solution. Correct? All those monosaccharides, aldehyde, ketones, right? All those monosaccharides, we have fructose, glucose, in which aldehyde and ketone groups are free, right? All those monosaccharides are reducing sugar, right? All those are reducing sugar, right? You must keep this in mind whenever anomeric carbon is involved in glycosidic linkage, it is non-reducing sugar. Clear? No doubt in this. One last point. Yeah.
So C1 and C2 aren't anomeric anymore, right? Because they don't have an OH and an OR. Like in sucrose.
Yeah, right.
Okay.
We do not have hemiacetal linkage here, and that is why it is acetal, and hence it is non-reducing. That is what I am talking about. If suppose we'll see some more examples. Maltose, if you see, there C1 and C2 are not involved, right? Means for both monomers, for both this thing, monosaccharides, anomeric carbon are not involved in maltose. For one it is anomeric, for other one it is the other carbon atom, not anomeric carbon. So if the molecule has any anomeric carbon which is not involved in glycosidic linkage, it is reducing sugar. C1 carbon is this for glucopyranose, C2 carbon is this for fructofuranose. Both C1 and C2 are anomeric carbon for these two structures. And hence these two structures are involved. Hence what happens? The molecule that you get sucrose is a non-reducing sugar. Non-reducing sugar also won't show muta rotation. Okay, another properties. Reducing sugar shows muta rotation. So these 3-4 points you should know. That is it. They ask direct questions on this, not more than that. Okay. Second, the second one we have maltose. Okay. Write down. It is formed by the condensation of two molecules of alpha D glucopyranose, in which C1 and C4 carbon are involved in glycosidic linkage. C1 and C4 carbon are involved in glycosidic linkage.
So could you repeat it?
It is formed by the condensation of two molecules of alpha D glucopyranose, in which C1 and C4 carbon are involved in glycosidic linkage. Okay, C1 and C4 carbon.
Yes, sir.
So,
Thank you.
two molecules of alpha D glucopyranose, correct? Both are alpha, so both OH on the first carbon will be down right here, H on the top, and then it is H on the top, H on the bottom, H on the top, and H on the bottom. Here we have OH, 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 and last carbon we have CH2OH. Here we have H, then H on the top, OH on the bottom, H on the bottom, H on the top, H on the bottom. On the top we have CH2OH, bottom we have OH, top we have OH, and that is it. So C1 and C4, right? So this is C1 carbon, anomeric carbon. C4 carbon is this, yes or no? 1, 2, 3, 4, 5, and 6. This H and OH involves into condensation, minus of H2O, and we get the structure of maltose, which is this. All other things will be as it is. Okay. This one you see, this is the anomeric carbon not involved in glycosidic linkage. This is glycosidic linkage. Glycosidic linkage. Okay. Anomeric carbon is free. This is a reducing sugar. Reducing sugar, and reducing sugar shows muta rotation. What all carbon atoms are involved? C1 and C4. C1 and C4. One more thing you must take care of. This corner here, these are not the carbon atom. Don't get confused, okay? Just a bond we have here. Finished?
So 1 minute.
So is it hemiacetal or acetal?
This one.
Yes,
This one
sir.
actually has both linkage. For this part, if you see, it has acetal linkage, and this part, it has hemiacetal linkage. So both kind of linkage is there.
Okay, sir.
Finished, right?
Yes.
Okay. Now the third last one in disaccharide is lactose. Write down. It is obtained by the condensation of one molecule of beta D galactopyranose one molecule of beta D galactopyranose and one molecule of beta D glucopyranose. Okay, one molecule of beta D galactopyranose and one molecule of beta D glucopyranose in which C1 and C4 unit are involved respectively.
So C1 and C4.
C4, yes. C1 and C4 units are involved respectively. Means C1 of beta D galactopyranose. I'll write down just a second. You are getting confused. We have beta D galactopyranose and alpha D glucopyranose. C1 carbon of this and C4 carbon of this. You know the structure of galactopyranose? What is the structure? You do not know, but you know the structure of glucose, right? And glucopyranose, galactopyranose, we know what is the relation. They both are what?
Epimers.
C4 epimers, right? So hence you can change the configuration at C4 carbon and you will get the structure of galactopyranose. Correct, right? So obviously these two are first carbon and this is the fourth carbon. So we have here galactopyranose. Beta D galactose, so beta means OH on the top, H on the bottom for the first carbon, then H on the top, then H on the bottom. But since it is galactopyranose, so at the fourth carbon, H should be here and OH should be here. The configuration will be ulta, right? Because it is what? It is alpha D glucopyranose, OH here, H here. Here you see H on the bottom, H on the top. Is it? Just a second. Okay. H on the bottom, H on the top, then H on the bottom. Then what we should have here for glucose, it is H over here and OH over here, right? So when you're trying to draw galactose at this carbon, the configuration you have to reverse. So here OH on the bottom, here it will be on the top. And then everything is same, CH2OH, H, OH, OH. This is also H, CH2OH, H and H. So this is alpha D glucopyranose, beta D galactopyranose. Okay. So C1 and C4 carbon involved into this. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So when this OH and this H is involved into this condensation reaction, H2O goes out and the product that we get is This is the structure of lactose, and this bond is the glycosidic linkage. Glycosidic linkage. Okay, again you see anomeric carbon is free. So it is what? It is
Reducing
sugar. Reducing sugar means it shows mutarotation. Glycosidic bond present between C1 and C4 carbon atom. Done.
Yes, sir.
Okay, so we'll take a break now. After this, we'll start polysaccharides. Sorry?
So shouldn't the anomeric carbon have an OH also?
Acha, yes, it is OH. Correct, no? Huh.
Yes, sir.
Take a break now. We'll come back at 6.
So shouldn't the OH be up there because it's beta? Oh no, sorry, it's
No.
alpha.
Beta is this side. Galactose is this one. Okay. This side we have galactose. I should not write it here. This is the part of galactose. Galactose is this. And this is alpha glucose.
So is galactose plus or minus?
It is alpha D. See, plus and minus again we have to check. I can't say like this. It's like I said, it's experimental. No. So I have to see alpha D or beta D plus glucose whether it is plus or minus. Okay, there's no idea of it. There's only one way to do this. Two way actually. You have to perform that experiment. If not, you just have to find this information in the book. If somewhere
Okay,
it is
sir.
given, then only you can say it is plus or minus. Okay, I
sir.
haven't seen this. It is plus or minus. Okay, yeah. Fine, guys. Take a break now. We'll resume the session at 6:50. Correct. Hello?
Yes, sir.
Yes, sir.
Okay. Yeah. Hello. So the last part of carbohydrates we are going to start with, and that is polysaccharides. This is not important at all. Only 2-3 things you should know, and we'll move on. We won't discuss much. Correct? Polysaccharides are what? Again, it is the polymers of monosaccharides. Monosaccharides. For example, we have starch, cellulose, etc. Okay. The general formula for polysaccharides is C6H10O5 N. Okay. 2-3 informations about starch you must remember. Starch is a white amorphous substance. White amorphous substance present in wheat, rice, potatoes, etc. Okay. On hydrolysis by enzyme, it behaves as a catalyst. Enzyme or amylase. Amylase is present in saliva, right? So on hydrolysis by these two, it converts into glucose. Eventually you will get glucose, and hence the test of this little sweet test we get for this. Okay, when we eat potatoes and all, we'll get little sweet test because of the hydrolysis in presence of amylase, which is present in saliva. Okay, these things they never ask in the exam. Okay, the only 2-3 things which is important for this starch we have regarding this properties, structure. Okay, so write down it has 2 components. The structure of starch has 2 components. 2 components. The first one is amylose. The first component is amylose. Okay, for this 2-3 properties you have to keep in mind, and the other component amylopectin, 2-3 properties of that is it. Okay, like amylose is a linear polymer. It has no branch. Okay, linear polymer, no branch, soluble in H2O. It is composed of, this point is the most important one, composed of alpha D glucose unit, in which C1 and C4 carbon, C1 and C4 are involved in involve in glycosidic linkage. Glycosidic linkage. The number of units in this just a second. The number of glucose unit is 60 to 300 glucose unit present into this. Okay, and its repeating monomer, which repeats in this is, since we have alpha D glucose, so we'll write down the structure of alpha D glucose, which is this. Okay, here we have this O, this bond, and this O, this bond. So this is the repeating unit we have, where this oxygen is present in this unit, and this side we have again the same thing, hydrogen. This is we have OH, H. This is we have OH, H. This is hydrogen. This is hydrogen, CH2OH. So this kind of 60 to 300 units we have, which are attached one after the other and forms this structure amylose.
Sir, could you move the previous slide 1 second?
Finished?
So, the polymer will terminate when there's a OH instead of a glycosidic linkage, right?
Discuss amylopectin and then we'll come back to this question. Wait, because this is the only one component we have seen, right? Another component also we see, and then we can answer that question. Done? Can you move on?
Could you go back to the previous slide just for 1 second?
Yes, sir. See.
Okay. The second component of this we have, we call it as amylopectin. In JEE, they haven't asked this question, but in NEET, they have asked this question. Okay, the starch-based question. Amylopectin. See, the first one is linear, so this one is a highly branched polymer. Amylopectin is highly branched polymer, complex structure. Polymer. Okay, insoluble in water, insoluble in water, composed of alpha D glucose unit And in this also, C1 and C4 carbons are involved. Number of units in this, units 300 to 600 unit we have into this one. Okay, but we don't have linear, but we have branch also into this complex structure, branch also present. Okay, starch as a whole, since you see all oxygen and the OH groups are involved into this. So starch as a whole is a non-reducing sugar. Okay, starch is a non-reducing sugar. Cellulose is also non-reducing. The another polysaccharide, cellulose is also non-reducing. Done. Okay, similarly, few informations, when you read NCRT, you'll see there is a cellulose, few points, how the glycosidic linkage forms, that you should know. But all these things are not important. Okay, they won't ask much questions into this. Okay, monosaccharides are the most important one in this chapter. Okay, now after this, we have to discuss the last part of this chapter, that is, protein. We have to discuss amino acids also you can say, and peptides. And peptides, correct? So proteins, the basic building block of protein is amino acids basically. Okay, write down, amino acids are the basic building block of proteins. Basic building blocks is protein. Protein has a very complex structure in which
Sir, could you repeat?
Amino acids are joined together by peptide linkage. Okay, peptide linkage, we also call it as peptide bond.
Sir, could you repeat this sentence?
Or peptide bond. Okay, so peptide forms by the condensation of two or more amino acids. Okay, second. No, it's not. Am I audible to all of you?
Yes, sir.
Rahul, it's not on mute.
Okay, no, so someone was asking doubts, so that's what I thought.
No, sir. Could you
hear me,
repeat
guys?
the sentence?
Can you hear us?
Yeah.
Yeah.
Yes, sir. Can you hear us now?
Rahul, yes, I can hear you. Am I was audible? No.
Yes, sir.
Yes, sir.
Sir, but can you hear us like that?
Now it's coming. I think some network problem was there. Your voice was not coming that time. Now it's fine, I guess. Any doubt you were asking?
No, sir. I asked us. Can you repeat the previous sentence?
Which one?
The one like what you told about.
No, just you tell me the last line you have written.
Oh, yeah. About the definition and stuff like that.
Definition of this amino acid, right?
Yeah.
I just said that. Okay, I'll repeat it. I said what amino acids, correct? Huh? Proteins. Huh? Amino acids are the basic building blocks of proteins. Okay. Protein has a very complex structure in which amino acids are joined together by peptide linkage. This is what I said. Amino acids are joined together by peptide linkage. Okay. So basically, to understand the structure of protein, however, the structure-based question they do not ask. Okay. But we'll see that how the structure forms. Okay. To understand the structure of protein, you should know what is amino acids and how the n number of amino acids combines together forms peptide linkage and then forms proteins. Okay, so first of all, we'll see what is an amino acid. Okay, like the name suggests, this is the bifunctional organic molecule. Bifunctional organic molecule. It has two functional group actually. Organic molecule. One is amino, that is NH2. NH2 amines, basically it is derivative of, and other one is carboxylic acid, COOH. Two functional group present. For example, you see, if I draw this structure, CH3CH, CH2NH2, CH2COOH, and here we have NH2. So this is an example of amino acids because we have amines group present, NH2, and COOH also present. Position of NH2, if you see here, this NH2 is present at beta carbon. Hence, generally we call it as this kind of compound, we call it a beta amino acid. Right, which we do not have to study. Beta amino acid we do not have to study because protein is mainly formed by alpha amino acid. Right, hence we consider only alpha amino acids. Right, on the protein forms by alpha amino acid. Even the naturally occurring amino acids are alpha only. Alpha form only exist naturally. Okay, so you see the general structure. General structure for amino acids we have is carbon with COOH and one amino group at alpha carbon, which is this only, one hydrogen, and here we can have any group attached, any G. Right, general structure is this, but there are few structures which does not follow the general trend. In NCERT, if you see, like I have already told you in the last class, that NCERT theory is more than enough for this chapter. You don't have to study much. Okay, so in NCERT, if you see, there are almost 20 structures given for amino acids. So those 20 you have to keep in mind the structure name, and the structure of that compounds.
So
that
what
you
is
have
G?
to. I'll tell you what is G. Okay, so that those 20 structures you must remember. First thing is that. Now this is the general structure of amino acids, alpha amino acids. This is the alpha carbon, yes or no? This carbon attached to the functional group carboxylic group, it is the alpha carbon. Hence, this compound is alpha amino acid. This is the general form of an amino acids. G can be anything. G can be anything. Okay. So this is, now this G, like I said, it can be anything, right? Suppose, for example, if you substitute this G, if you substitute this G as hydrogen, then the name of the compound is glycine. This is an amino acid, alpha amino acid, glycine. If this G is methyl, then the name of the compound is alanine. If this G is CH2PH, then the name of the compound is phenylalanine. Are you getting it? So this type of 20 odd structures given in NCERT that you should know. We'll see some more structures. Okay, one by one we'll see that. Copy this down first.
So why is that alpha?
Because the proteins, the structure of protein, if you see, it is made up of alpha amino acid only. That's why we are considering only alpha amino acid, and that is there in our syllabus, only alpha thing.
Yes, sir.
Okay. The carbon which attached to the COH group is the alpha carbon, and amino group attached to alpha carbon, hence it is alpha amino acid.
So when is it serine?
We'll discuss that. We'll discuss almost 8 to 10 structures. Wait.
So we have to remember all those 20 structures.
20 structures given. In that, few are important. I'll tell you which one is important. Okay.
Okay.
And why it is important, that also we'll discuss in some time. Did you copy this? Okay. Next, you see classification of amino acid. Classification of amino acid. Three different classifications we have. 1, 2, and 3. Three different classification we have. The first one is acidic amino acid, acidic, then we have neutral, and then we have basic. This acidic, neutral, and basic is based on the number of acidic group present and basic group present. Basic group is what in amino acid? NH2.
NH2.
And acidic group is COOH. So if we have more number of COOH, then it is of acidic type. If we have more number of NH2, then basic. If it is equal, then neutral. Got it? So it's based upon the number of acidic group present and basic group present. It is not the actual behavior of the compound, whether it is acidic or basic. Okay. So for example, acidic compound, let me write down here, are those amino acids which has more number of acidic group present. Number of acidic group present. For example, we have the pattern is this NH2 CCOOH and H, right? And this group, this G, if you place this as CH2COOH, then the name of the compound is aspartic acid, and it is an acidic compound, acidic amino acid. Okay, if you place this as NH2 CCOOH H, and here we have CH2CH2 COOH. The name of this compound is glutamic acid. Glutamic acid. Okay, what are the basic amino acids? Basic amino acids are those in which the number of basic group is more. Simple, right? The number of basic group is more. For example, we have NH2 CCOOH H, and here we have CH2 4 times NH2. This is 4 times, okay? CH2 4 times NH2. The name of this compound is lysine. Got it? Basic.
So how do they expect us to remember all of these?
You don't have any other choice actually, because sometimes they ask this question, which of this acid is acidic or basic, like that. So if you do not know the structure, you cannot do that. Okay, and yes, it is difficult to memorize all this. That's why I have given you this pattern. G, only that G you try to understand. For lysine, what is G? For glutamic, what is that G? Okay, you need some practice. No, you have to revise it continuously. Then only you will memorize it. I would suggest what? Suppose you have test, right? Then you should revise this once properly before the test. Suppose half an hour, like one day before, obviously you'll revise the entire syllabus. But suppose half an hour, after half an hour, you have to write down the test. Just go through these structures. Okay, before the exam, just go through these structures. Half an hour before, 1 hour before, like, or one day before. Okay, so there are few things in chemistry which requires the revision at the last moment. This belongs to that particular sections. Okay.
Yes.
But yes, you should know that what are the topics you have in this particular type, that you should those topics you should revise just before the exam. You should have this idea. Okay, right? Lysine. So neutral is what? Neutral means number of acidic and basic group is same, right? Equal number of acidic and basic group. And basic group, like previous only we have seen the example alanine, okay, glycine, phenyl alanine, all those are neutral amino acids, correct? Some more structures we discuss here. Suppose we have NH2 carbon COOH hydrogen. If you place this group as CH2OH, the name of this compound is serine. Okay, if instead of this OH, if you place SH, CH2SH, slight change we have here, COOH NH2 H The name of this compound is cysteine. Okay, the important structure which does not follow the general trend we have, the pattern we have, is this. Here we have COOH. Okay, this compound, the name of this compound is proline. This is important because it does not follow the general trend. This is important, right? In all the structure you see, all are optically active. This carbon is chiral in all the compound except the first one that I have given, which is this. Glycine is what? When hydrogen present over here. So this glycine is what? It is optically inactive. That's why this is also important. This is the only one which is optically inactive. Hence this one, proline, you must remember. Got it?
So what's the spelling of the first amino acid?
SERINE. Okay. Now, one note you write down. These amino acids exist in two stereoisomeric forms. Exist in two stereoisomeric form, D and L. However, all naturally occurring amino acids belongs to however all naturally occurring amino acids belongs to L configuration. L configuration. Keep this in mind, okay? Protein exclusively consists of L amino acids. Just information you should keep in mind.
So here, how do we tell between D and L?
Sorry?
So how do we tell between D and L over here?
D and L. D
Yes,
and
sir.
L is that only. That C. We have discussed first class, no, glyceraldehyde, OH on right side, D and L.
So not all of these have
That D and that L, because there also I have told you that we have a different, a system to determine the configuration for carbohydrates and amino acids. So that D and L is valid for carbohydrates and amino acids, which we have here.
This is for all amino acids, right?
All amino acids.
So here, how do we tell if it's D or L?
In this, obviously, when you write COOH on the right side, it is D. When you write this on the left side, it is L.
Okay, sir.
Okay. Advik, I didn't get your point. So if the protein was made of D, then it wouldn't be the same. What? So if it has D, it cannot be used by the body. See, it's not like it cannot be used. That we cannot say. We have to see how the the properties of the amino acid changes. Okay. Yeah, it depends upon the properties. When you change the configuration, right? How the properties changes, right? It depends upon that. Directly we cannot say. We cannot say a general thing for this. Maybe for some molecule it is possible, for some it is not possible. Both way it may go. Depends upon the properties of the molecule, to what extent the property changes. Based on the configuration, we are just talking about its behavior towards the plane polarized light. Okay, like you see, acidic behavior won't change that much. Basic behavior, because we have two different groups, that won't change that much. Configuration here represents the behavior towards the plane polarized light. Okay, that is what it means. It is still, if COOH you write on the right side or left side, it is still carboxylic acid only. So acidic property you see, that won't affect that much. It would be same only, almost. So it depends upon what group you have and other things. Okay. See, chemical properties won't change much, right? It would affect the pH of the solution. We are going to see one more topic here, that is Zwitter ion, right? So there we see there's an isoelectric point. We talk about pH over there. So that configuration may change the pH over there for Zwitter ion, right? But that change won't be that great. Okay, that is what we can say. As far as the configuration is concerned, we mainly deals with the behavior of the molecule towards the PPL, plane polarized light. But still the molecular formula is same. So physical properties, chemical properties won't change that much. Okay, yes. So the next thing we are going to understand is Zwitter ion. Write down the heading, Zwitter ion. See, Zwitter ion is what? It is the dipolar neutral ion. Okay, neutral ion. There must be charge, positive and negative charge present. But that is equal. Okay, so write down. This is Zwitter ion, write down. It is dipolar neutral ion which exist in solution when amino acids are dissolved in the solution, usually aqueous solution. We take amino acids are dissolved in the solution. Now you see this example of amino acid. We have NH2, C, then we have a group here, COOH and H. So when you dissolve this in water, right, H2O, then what happens? This acid has the tendency to lose H plus ion, and hence it converts into H2N COO minus GH and H plus will go out. Okay, in solution, this is the tendency we have. But at the same time, this NH2 is basic in nature. So this has tendency to accept this H plus. And hence it converts into what? A dipolar neutral ion, which is this G, and this H will be as it is. This dipolar neutral ion that we have here, this is Zwitter ion.
So but this will be highly unstable, right?
In solution, it is there, but that depends upon the pH of the solution also. Yes, obviously. Stability, obviously, we compare relatively, we say, right? So
Yes, sir.
this molecule and this molecule, you see, this is not that stable. But in the water, this acid has the tendency to lose H plus, and this will take H plus, and this is the property.
Okay.
Okay, but again here you see tendency to lose H plus or gain H plus by NH2 here. It also depends upon the pH of the solution in which it is kept, right? So write down the next line here. The structure of amino acids depends upon the type of the solution, means whether it is acidic or basic, the type of the solution, whether it is acidic or basic, and the pH of the solution. pH of the solution.
So could you repeat?
The structure of amino acids depends upon the type of the solution, in bracket you write down acidic or basic, and the pH of the solution in which it is kept.
Thank you, sir.
Okay, now you see this ion that we have, that we are calling it as Jupiter ion, COO minus, with one group attached here, and we have NH3 plus. This is Jupiter ion, right? This exists in mainly neutral solution. Neutral in the sense we can say the tendency to lose H plus by COOH, and the tendency to accept an H plus by NH2, if it is equal, then this ion will exist. This neutral ion exists, which we are calling it as Jupiter ion. If both the group, acidic and basic group, has equal tendency to gain or lose H plus ion, then this dipolar neutral ion exists, which we call it as Jupiter ion. Okay, but if the solution pH is more or less, then depending upon the pH of the solution, this Jupiter ion exists into either anionic form or cationic form, right? But anionic and cationic form are not Jupiter ion. Jupiter ion is always neutral, this one that I have drawn. But this ion exists in the form of an anion or cation depending upon the pH of the solution. Okay. Now suppose we have very high pH. High pH means what? Acidic or basic?
Basic.
Basic, OH minus. So this OH minus has tendency to take H plus. So this will take H plus from this NH3 plus, and it converts into CCOO minus this NH2 NH plus we have H2O. This is what it forms. This is the anionic form. Okay, so the amino acids may exist in this form depending upon the pH. If the pH value is very low, it means what? It is acidic, H plus, then this H plus will get attached on this CO minus. This forms what? H3N plus C group, COOH and H. This we call it as cationic form. Okay. So the amino acids may exist in these three forms in the solution depending upon the pH of the solution. Correct? Right. Now the pH value where the amino acids exist in the form of Jupiter ion, the pH value at which this Zwitter ion exist is called isoelectric point. Electric point. Okay, write down this.
Sir, is like the actual range in our portions,
Range in the sense?
like the pH range.
No, you don't. You obviously you cannot memorize the pH for all the amino acids, correct? But few examples I'll give you, and their isoelectric point value, the pH value, I'll show you what all things are there. But yes, you don't have to memorize that pH value. Obviously, we have some range, some pH value around that only. It will exist in the form of Zwitter ion, but that you don't have to memorize. Little bit of idea you will have. If it is acidic, then the pH value will fall in the acidic range, less than 7. If it is basic, then more than 7. If it is neutral, then also it won't be 7, but it is close to 7. Those kind of idea you will have. Done this one? So suppose here you have a beaker in which we have a solution, and the solution contains amino acid into this. Okay, 2 electrodes are placed here, and this electrode is connected to the positive and negative. It means basically a battery. Okay, so depending upon the pH of the solution, the amino acids either exist in this form or in this form or in this form. So if it exists in the neutral, in the cationic form, then this will move towards the negative electrode. And if it is in, and solution is conductive in that case, okay, we'll have the deflection here. Since current is flowing, we can say that. Negative charge, if it is there, it will move this side, right? Again, solution is conductive and it shows the deflection over there. So if you change the pH value, and when there is no conduction, no deflection, it means this amino acids exist in neutral form, this form, plus and minus both charges present. So in this form, it won't move either this side or this side, and hence no conduction. That value of pH is the isoelectric point. Correct? Few examples and its isoelectric point we'll see. The first one is CH2 COOH. See, this one is acidic, correct? Acidic amino acid, 2 COO group attached. And the name of this compound I have already given you. It is glutamic acid. Its isoelectric point is 3.22. Since it is acidic, so less than 7 must. Okay. Another example you see, we have COOH, and here we have CH2 4 NH2. This is basic, so its isoelectric point also fall in the range of more than 7 to 14, 7 to 14 basically. So this value is 9.87 for this, since it is basic. If you take a neutral one, for example COOH, here we have CH3, alanine, NH2, H. This is alanine, And according to the number of acidic and basic group you see, it is neutral, but its value of pH is 6.02, not exactly 7, because the COOH carboxylic group has more tendency to lose H plus than the gaining tendency of this NH2. That's why it is slightly acidic in nature. Done.
Sir, could you repeat why alanine is acidic?
See, we have acidic group COOH and basic group NH2. So one has tendency to lose H plus, one has tendency to gain H plus. Correct?
Yes, sir.
So if these two tendencies are equal, means the tendency to gain H plus for NH2 is equal to the tendency to lose H plus for COOH, then it is completely neutral, correct?
Yes, sir.
But COOH is dominating over here. It dominates the the effect of this molecule. Means it loses H plus ion continuously, and with the same rate NH2 is not taking H plus. Hence the solution becomes slightly acidic.
Yes, sir. Got it.
Okay, these 3 points here. Now there's 2 things you write down into this: essential amino acids. Essential amino acids. Essential amino acids. These are the amino acids which cannot be prepared by body, which cannot be prepared by body. For example, lysine, phenyl, alanine, just definition is there. Lysine, phenyl, alanine. Cannot be prepared by body. Lysine, phenyl, alanine. Next, non-essential amino acids. Non-essential amino acids. These are the amino acids. These are the amino acids which is prepared by body itself, which is prepared by body itself. Example, glycine, alanine. Example,
alanine. So can you repeat the examples for the essential ones?
phenyl, alanine, and lysine. Non-essential is glycine, alanine, serine also you can write. Non-essential.
So how is alanine both non-essential and essential?
It's not alanine.
No, that's phenyl.
First one is phenyl.
First one is phenyl.
Yeah.
Could you repeat?
Essential one is phenyl. Just a second. The essential one is lysine, phenyl, alanine.
Oh, the same one word.
Yeah. Non-essential one is glycine. What is glycine? What is G over there in glycine?
Hydrogen.
Hydrogen. Okay. Glycine is what? Optically inactive. Not chiral. Okay. Fine. After this, we have to see protein formation. Okay. But before that, we'll see one question. Try this one. The specific rotation of alpha glucose Write down. A specific rotation of alpha glucose is plus 112 degree. This kind of question sometimes they ask in JE. Okay, 1 not tough, just you need to know how to do this kind of question. And for beta glucose and for beta glucose is plus 19 degree. Right, alpha and beta glucose will get the equilibrium mixture, and for equilibrium mixture it is 52.7 degree plus 52.7 degree. Calculate the percentage composition of anomers in the equilibrium mixture. Yeah, that's right, Ruchil. Vikas, correct. No, Akshay, that's not right. Pradyut, that's not right. Dhruv, correct. Who is this KTG? Wrong. Sai, correct. Okay, Kirtan, that's wrong. See, specific rotation is simple. Suppose this alpha form has composition uh, alpha only, and its composition I'm assuming beta, right? So the equilibrium mixture has a specific rotation 52.7 is equals to contribution of this and contribution of this, right? So contribution of this is what? Alpha into its specific rotation plus 112 plus beta into its specific rotation plus 19 divided by 100. And we also know alpha plus beta is equals to 100. So we can solve this equation. Another way, what you can do, that this beta form is more stable, correct? Beta form is, suppose you have options given like this, okay, A, B, C, and D. Okay, the correct answer here is 36.2 is alpha and rest is beta, which is 63.8. Suppose one more options we have like this 63.8 and 36.2, and two more options given like this. Okay, we know the fact that beta glucose is more stable than alpha. So obviously the composition of beta will be more. And since the composition of beta is more, that's why you see the average value of this two, 19 plus this divided by 2, which is coming out to be more than 60 approx, but the value, equilibrium value is less than the average value of this two. It means what? Obviously the beta glucose composition should be more, then only the equilibrium value will be closer to beta, otherwise it will be close to alpha. Yes or no? Are you getting this point?
Yes, sir.
If alpha is more stable, correct, then alpha tries what? That the equilibrium value should be close to the value of alpha. If only alpha is there, then it will be 112. If only beta is there, then it will be 19. Since we are mixing the two, or in the mixture we have both present, so both wants the specific rotation to be 112 and 19 respectively. But the mixture has the two, hence the one which is more stable, that dominates the other, and hence the equilibrium value will be closer to the more stable one, and hence it is lesser than the average value of this two, right? If suppose this form is more stable, then the equilibrium value will be more than the average of these two. Okay, so with this information you can eliminate options sometimes. Okay, alpha value is less, beta is more, so probable option is this at least you can eliminate easily. So you don't have to do the calculation, you can avoid
So,
it.
but generally they'll give two options which are both above 50, like the.
That is also possible. They can give you options like that. That is also possible. But in that case, suppose you have one more option. Suppose I'll give you this one 40, this one, and this is 60. Then you cannot do this. Okay, you can eliminate this and none of this. Suppose if you have none of this, chalo won't do. And suppose one we have 82 and other one only 80. Like this, suppose to give it. So obviously you can eliminate B and D, right? Then you can you are left with two options. Okay, then you have to do a little bit of approximation, and then you can find out which one is the closer one. Okay, but yes, with this data you can eliminate 2 or 3 options sometimes. Okay, directly you will get the answer. You should have this idea also. Got it?
So how is alpha plus beta 100? Like, how do we know that?
Composition we need to find out. No, so out of 100, see the percentage composition is given. So we need to find out of 100 what is the percentage composition we have.
Okay, sir.
Correct. So I wanted to show you one more question, because protein structure I don't want to start today. It will take some time, then I have to leave in between. One more question we'll see, just a second. Okay, you see this structure. I'm just sharing this just now. You see this structure. Answer may be multiple correct. Correct, Ruchir. Ruchir Parekh. Pradyut, right. Advik, right. It's multiple correct, Vikas. No, Ruchir. Ruchir Singh, it's wrong. Chaitanya, it's wrong. Correct. Varun, that's right. See, reducing sugar means what? You just need to check anomeric carbon, if it is there or not. Right? Anomeric carbon you have to check. Yes.
One option I put by mistake, I didn't see.
Yeah, right. No, it's correct. Okay. So obviously you see option A is correct because this carbon is the anomeric carbon. Right, anomeric carbon. This carbon also an anomeric carbon, hence it is also a reducing sugar. This is acetyl group, right? It is acetyl molecule. These two are hemiacetal structure. This is also hemiacetal structure, right? And anomeric carbon is present in hemiacetal only. This part obviously it is acetyl, but here we have OH and OR present. So this carbon is the again anomeric carbon. Hence the answer for this question is A, B, and D. Got it? Got it? So this kind of questions you get. This chapter is not that tough. Okay. Right. So biomolecules, polymers, you are going to get one questions. This kind of questions you can do easily. But yes, you have to revise these things on at times. Otherwise, you'll forget this. Anyways, guys. So next class, yeah.
So in option C, if we replace the COH and the OCH3, it will become reducing, right?
Wait. What replacement we should do?
If we replace the C bonded to the OH and the C bonded to OCH3.
C bonded to OH. Here, the saying.
Yes, so like if you just shift the entire thing, right, will it become reducing?
Here and this here.
Yeah.
Okay, this here and this here, then the entire is the molecule you are changing, no?
And yes, I'm changing the molecule and I'm asking if the new molecule will be reducing.
Yeah, it also possible, because you see, reducing thing is there. When we say reducing sugar, it means it can reduce tolerance reagent, and tolerance reagent can be reduced by aldehyde. Okay, so when you have OH over here, like we have in this carbon OH, this is 2 degree OH, right? So this can reduce aldehyde easily in alkaline medium. Okay, it's possible. So reason is that you have to understand the reaction over there, which we'll see later on in the next chapter, right? So when you place this OH here, this carbon, suppose H in OH, if you place over here, it is not a carbohydrate in that case, because we have then ether, one ether present over here, right? But yes, that compound, if you say it is reducing or not, it may reduce tolerance reagent. That's fine.
Okay, sir.
Okay. So that is the thing, these three things you have to keep in mind. So next class, guys, we'll start with the structure of protein. Okay. DNA and RNA, we cannot, it's not important for JE and all, right? However, they have asked 1 or 2 questions in the previous year, like 6-7 years back, 2013 or 12, they have asked 1 question on this. Okay. So I would suggest at least NCRT you must go through for DNA and RNA, but not that important. Okay. Protein structure is also not important. They haven't asked any question, but we'll go through one. So next class we'll finish the structure of protein, and then we'll probably finish polymer also. Small chapter we can finish in like 3 or 3.5 hours. Okay. Okay, guys, thank you. So on Learnist, 1 assignment has been uploaded for this biomolecules. You must solve that.
Sir?
Yeah.
So by when will you send the video for this class? Because I missed some 5 minutes. Yeah.
Yeah, this one I'll send by tomorrow, because this process, it takes some time to get recorded. Okay, because it takes some time for processing. So in 1 hour it is done. Then I'll share this to Dheeraj sir. He will upload, and then I can share. So tomorrow you will get it. Okay. Yeah. Oh.
Yes. Thank you, sir.
Okay, guys. Thank you. Yeah.
Thank you, sir.
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 Thank you, sir.